Okay, so what you see in front of you is a modified alkane, and we see a halogen or two halogen atoms bound to it. Now, how many valence electrons does a halogen have, Alphys?
Not too sure actually.
Come on, mate. Junior science. How many electrons would a halogen valence shell have? It's a group
It's
7
7.
elements. Good, right? It's got 7 electrons. So how many electrons does it need to form a stable octet configuration, Gerald? A halogen.
Just one.
Just one, right? So in that sense, a halogen operates very similar to a hydrogen atom. Hydrogen has 1 electron, halogen has 7, but they both have the same end goal. They both want 1 additional electron. So what you'll notice is in many HSC questions, a halogen can occupy the exact same position that a hydrogen can. Okay, so the way we treat haloalkanes is exactly like your normal alkanes, and the important point here is your halogens get equal priority. They're treated as exact equals to your alkyl groups. So your methyls, your ethyls, your propyls. Okay. Now, Annette, how do we name a halogen group? So we see this is a bromine. How would I name this if it was a side chain, as you see here?
You change it to bromo.
Good. So you take the ene out and you just add an O. So it goes from bromine to bromo. Now, Mithilesh, this is chlorine. How would you name it if it was a substance? Yeah, chlor. Very good. And Riasat, what if I had an I here? What would you call that? Good, perfect, right? Otherwise, the exact same principles are. Yeah, good job. The only difference, actually, there is no difference, is when you name it, make sure you still follow the same principles. You name it in alphabetical order. So this bromine would have priority over, let's say, if there was a methyl group here, because M comes after B. Okay, so given all those points, here you go. Here's your first question. Name this haloalkane. Follow the exact same principles you did. I want you to hit your raised hand icon as soon as you get an answer. All right, let's get started. Maher, what's the first step in naming any alkane or haloalkane?
Find the longest carbon chain.
Good. Gerald, what do you want to do before that? You see this is a skeletal formula. What might you want to quickly do to make sure you don't make silly mistakes?
You would want to change it to the expanded formula.
Good. And Gerald, do I need to draw the hydrogens, or is it sufficient for me to just draw the carbons as I'm doing here?
You can just draw the carbons. That should be fine.
Good. Yeah, right. And the reason is, if you've recalled, we never look or count carbons when it comes to naming, right? Now, let's just make sure that we've done it correct. So this isn't the longest main chain, but I'm just counting across 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. At the second carbon, there's another carbon. At the fourth carbon, there is a bromine. And at the fifth carbon, there's a chlorine. So you should mentally do that in your own head. Now, how do I name this compound? So Alphys, first step.
Okay, so what Mahi said before is find the longest main carbon. If you do that, on
And
that.
what's the next step after that?
You find the left to right, then right to left.
Good. 1, 2, 3, 4, 5, 6, 7. And then go right to left, which is 1, 2, 3, 4, 5, 6, 7. Now, reset. Which direction am I going to go? So what I'd advise you all to do now is circle the substituents too, because in your counting, you might miss a certain substituent, especially if there's a lot. So reset left to right and right to left. Which one gives me a smaller number?
Left to right does. So left to right gives 2 plus 4 plus 5, which is 11. Right to left gives 3 plus 4 plus 6, which gives 13. So left to right.
Good, right? So we're just going to highlight, since we're going left to right, we're picking the blue. So we'll circle the blue. All right, good. Now, Mithilesh, I'd like you to name this compound.
Okay, I got 4 bromo dash 5
I want you
chloro.
to tell me the dashes as well. 4
Okay,
dash
4
bromo.
dash bromo dash 5 dash chloro.
Yeah.
Dash 2 dash methyl heptane.
Good, perfect, right? Not too hard at all. Good. So as you can see, we're treating it just like an alkyl group, so never forget that. And when it comes to naming, we're just going to give it alphabet priority. Okay, good, perfect. So not much difference there. So I think we can probably stop naming your haloalkanes. I might give you one example. Then we'll go to how to draw an alkane very quickly. So we'll go to maybe, sure, we'll try this example here. This one, I'm not going to show you how to name it. I'm just going to see our final answer. And if we all agree, we'll move on from this question. So as fast as you can, you should be able to do this in under a minute. So I'll time you all now. About 30, 40 seconds, I'll ask someone to name it for me. Good. Joe, got an answer? What is your answer?
1 bromo, 1 dash bromo dash 3 dash chloro dash 4 dash methyl pentane.
Annette, agree, disagree?
I disagree.
Oh, we have some contention. All right. Annette, what's your naming?
I got the same. I just didn't get 3. I got 2 for the chloro.
2 for chloro. All right. And last person with a hand up, Reset, what did you get? Option 1 or option 2?
Option 2. 2 chloro.
Okay. 2 chloro. All right. Let's have a look and understand this. So remember, first step, whenever it looks funky, always convert it to expanded structural. So I just like underlining the carbons because it can get quite messy given that there are so many different atoms that are all in conjunction with one another. So 1, 2, 3, 4, 5. And what I can see is second carbon has a methyl group, so I'm going to draw a carbon there. Then what I can see is the first, second, third, fourth carbon has a chlorine. This isn't the fourth carbon necessarily, but just the fourth from what I've numbered it. and the fifth has a bromine as well. Good, so I can clearly see from here, I can either go left to right and right to left, and I can see that Gerald went right to left because his bromo has the first position. That would make this 2 chloro rather than 3 chloro. Does that make sense, Gerald? I think that was just a silly mistake. Can you hear me fine?
Yeah, it was just I mislabeled one of the chlorine. Yeah, that's what we.
Good. All right. Yeah, just make sure, because I think you'll realize by now, naming all of this is easy. The only time you're going to make a mistake is silly mistakes. So never disregard it. It's just a silly mistake. Make sure you don't make a mistake at all when it comes to naming. Good. All right. So I think we can all agree there should be 1 bromo, 2 chloro. Good. All right. The next point is just doing all of these questions as you go. What you should be doing every week is, once you get your booklets, doing all the questions for every lesson. So make sure you're not behind with your workbook at all. And that way you'll be on top of your work. All right. I think on that note, we'll touch upon cyclic hydrocarbons. Now, there's not much to mention just now for cyclic hydrocarbons, but I just want you to understand cyclic hydrocarbons occur when the main chain forms a continuous loop, as you can see here. There's no start or finish, right? And just like alkanes, we have 3 homologous series of cyclic hydrocarbons. We have your cycloalkanes, your cycloalkenes, and your cycloalkynes, just like your linear family. Now, I guess the only difference is their formula and naming are slightly different. And let's talk about very briefly the formula, right? What's the formula of this cyclic hydrocarbon? This one right here. CH, what are the numbers? You can quickly count and tell me. It's C6, what's the H? Quick.
12.
Good. Now, does that align with your understanding of a linear alkane? Is that the exact same formula that a hexane would have? Because this is a cyclohexane, right? Now, Annette, what's the formula of hexane, and why is it different to cyclohexane?
Well, it's different because since the carbons are linked in a ring, like you lose 2 bonding points.
Good. So typically, if this was a linear chain, this would be the first carbon, etc. I'm just picking an arbitrary point, and that would be the last carbon. But since they've formed a chain, what happens is we use up 2 more bonding sites. And so what that does is it subtracts 2 from the number of hydrogens. So what you'll notice is that cyclohexane has exactly 2 less hydrogens than its linear counterpart, which is hexane. So that means the general formula of a cycloalkane is CnH2n, but without the +2, because there's 2 less bonding points. Now, does anyone know what the general formula of an alkene is? Has anyone read ahead? What's the general formula of an alkene?
2n, C, and
Good,
2n.
CnH2n, right? The same principle applies. Since a linear alkene is CnH2n, a cycloalkene will be CnH2n subtract 2, 2n minus 2.
Prithvi,
Yeah?
when you mean by read ahead, we didn't get the actual book.
Yeah, you haven't got your books for Mod 6 because you haven't come and sent it yet.
Oh, we haven't got it online as well.
Oh, you haven't got your online access to the booklets?
Yeah.
What did you have your online access via? Was it via the website or Google Drive?
By the website.
Because they should all be on the same page. So there should be a Mod 6. What I
There's a Mod 6, but there's no
one
Mod
of you
7.
now. Oh, there's no Mod 7. Okay, so
Yeah.
what I'll get you guys to do then is right now, I think some of you might have admin, all of you should have admin's phone number. Just shoot them a quick message requesting the booklet up, and I'll do so as well, just to make sure you guys get access. So you should get access by tomorrow. Thanks for letting me know. So okay, great. Good. All right. So within the next 2 days, you get access. If you don't by, let's say, Friday, send me a quick message. Okay. Good. All right. So what would the formula for an alkyne be? A cycloalkyne. Gerald?
CnH2n minus 4.
Good. So an alkyne is typically 2n minus 2, so now it's going to be 2 less bonding points, so 2n minus 4. Very good. That's one point. Now the second point is when it comes to naming. So I want you to give this a go. If I was to add a chloride here, and I want you to name that, and I want you to also name it. How would you name it if I was to add a chloro here and a bromo here? I'm going to make your life a little bit harder. First example, second example. When you get an answer for option 1, raise your hand. Annette, what's your answer for option 1? What would you call the hydrocarbon you see in front of you?
Chlorhexane.
Come on. Are you sure? Disagree with that? What would you call it? Very close.
Chlorocyclohexane.
Good. It's a cyclic hydrocarbon. If you just call it chlorohexane, then you have to think about this. Coming from the name, if I were to draw this out, I'd go, well, the main chain is hexane, and they've said there's a chlorine. They haven't told me where it is. I'm just going to add it there. And that is nowhere near what you see in front of you here, right? So who agrees? Should we add a 1? Should we call it 1 chlorocyclohexane? Why not? Now remember, the principle of IUPAC is to give things the smallest, shortest name with the simplest numbers. IUPAC is all about keeping it simple. Now, I want us to all ask ourselves, would there be a point in calling this 1 chlorocyclohexane? Mahir, what do you think? Should we call it 1 chlorocyclohexane or just chlorocyclohexane?
1 chlorocyclohexane.
Now, to answer my question, the way you answer it is you have to ask yourself another question. If I move this chlorine, what would it be called? So right now, Mahir is saying this is 1 chlorocyclohexane. Mahir, if I move the chlorine to this position, what would you call it then?
The same thing.
And what if the chlorine was there? What would you call it then?
Oh yeah, true. The same
There
thing.
you go. Okay, so the point is, if you move this group around, you get the exact same name. So there's no point in putting a number in front of the alkyl group. So that's a little consideration you have to make. Yeah.
What if there's more than 1 chlorine? What would you do then?
And restart that takes you to. You tell me. So again, just to summarize, everyone, for option 1, you don't put a prefix in terms of the number. It's just going to be chlorocyclohexane. The number is redundant. So maybe just get a red pen and write number redundant with 1 alkyl group. Okay. And restart, since you asked, here's your question. Question 2. What would you call this? When you're ready, say your answer out loud.
Bromochlorocyclohexane.
Now, again, restart, you've straight away gone to not using numbers. But remember, if you want to ask yourself, do I need numbers in front of these groups? You should move the groups around and see whether it changes the name, right? So let's draw this in expanded formula again. Like I said, I don't like looking at skeletal formula. It's confusing. So draw the expanded formula. There's a bromine here. There is a chlorine here. Now, if I move this chlorine, so I'm just going to draw a ring form now, just to save time. But if I move the bromine here, and if I move the chlorine here, restart, according to your naming, what would the structure on the right, sorry, it's just loading. What would the structure on the right be called? So you've called the structure on the left bromochlorocyclohexane, what would you call the structure on the right?
Right, it would also be bromochlorocyclohexane by my name. That's wrong.
But do you?
So yeah.
Yeah. Okay. So I like how we're using thought principles. That's what makes organic chemistry a little bit challenging. There's no memorization here. Whoever memorizes is not the smartest person. It's the person who can use thought experiments and think about this, right? Learning how to think about chemistry is what makes this module a little bit more challenging. That means you must number it. But we can't go left to right or right to left. There's no starting point. So my question to you is, what number do we give these compounds? Any ideas?
Maybe bromo -3 chloro cyclohexane.
1, 2, 3. Sorry, what did you call this? Bromo -3 chloro?
I meant 4.
So could you repeat the entire name just so I can jot it down?
Bromo -4 chloro cyclohexane.
1, 2, 3, 4. Good, but I would number both of them. That would just be the only difference, right? So you can't just selectively pick numbers when you want to. You either give the numbers entirely to the entire compound or you don't number the alkyl groups. In this case, as you can all see, the position of the halogen groups matters because if it moves around, it forms a completely different compound, right? Whereas in this case, if this chlorine is jumping around, we just have to rotate that same compound like a clock and you have the exact same molecule. So here the issue is when you move the groups around, it forms a different molecule, so we must number them. So the answer is, it's the same as with linear alkanes. If going left to right and going right to left gave you the exact same number, you would then pick the direction that gave the alphabetical first group priority, right? In this case, bromine comes before chlorine, so we're going to make this carbon number 1. And then we're going to find the direction that gives the second alkyl group the smallest number. So that would be, you can either go up or you can go down, but the 4th carbon will always have your chlorine. So this will always be 1 bromo -4 chloro cyclohexane. Make sense? Okay, so just to elaborate, for methyl, you wouldn't not include a number here, but then include a number here. You either completely include numbers or you don't include the positions. Okay, good. Good job. We'll come back to cyclic hydrocarbons because they come up back in reactions, but for now, that's everything we need to cover. Any questions, everyone? Good. All right, let's move on to our alkenes. So alkenes are a completely different homologous series because they have a completely different bond. Instead of the carbon-carbon single bond, they have a carbon-carbon double bond. Now, we call alkenes, pretty much we call everything other than alkenes unsaturated. And we call our alkanes saturated. And why do we call alkanes saturated? And why are alkenes and alkynes not saturated?
Well, alkanes are saturated because they have the most number of hydrogens that you can have in a hydrocarbon.
Good. So per carbon, your alkanes have the maximum number of hydrogens attached. So for every carbon, it's bound to the max number of hydrogens possible. Now look at what happens, everyone. The second you add a double bond, that uses up one bonding site for each of the carbons. And so now the carbons can't bind to the maximum number of hydrogens. And it gets even worse. When I convert this into a carbon-carbon triple bond, now what you'll notice is I lose another bonding site per carbon. So whenever you have the sub-maximal number of hydrogens per carbon, so that's with an alkene or an alkyne, you call it unsaturated. So a key point is alkanes are saturated, alkenes and alkynes are unsaturated. Okay. Now, who can explain why that matters? Like, when do you hear the word saturated and unsaturated in real life? It comes down to health. Come on, what do we got? Gerald, when do you hear the word saturated and unsaturated?
I'm not too sure. Maybe like fluids inside the body. Like if you have like a high concentration of like carbon dioxide in your
Close.
blood.
I like the logical thinking. I like the logical thinking. It's fats, right? You should all be looking at this, right? Saturated fats are horrendous for you. In fact, trans fats, which are highly saturated, they immediately go to the heart, cause heart disease, and they're the number one cause of death on this planet, right? Even worse than COVID. So lower your saturated fat intake. That's one thing you learned about life from today's chemistry class. But key point here is when things are unsaturated, it's a bit counterintuitive. When you have a double bond or when you have a triple bond, it's actually easier to break that bond. And so it's easier for your body to break down unsaturated fats versus saturated fats. And hence why your saturated fats are bad for you. We'll come back to the bonding and reactivity part of things, but for now, that's just unsaturated and saturated in a nutshell.
Wait, I don't really understand how it's unsaturated.
Sure. So what does saturated mean to you?
What do you need? Just more like diluted or something like that.
No, not at all, not diluted. So saturated, think about this, right? If you're, let's say you're on Instagram, if you're trying to change saturation for a picture, you're adding the maximum amount of color you can for that picture, right? Saturation is the maximum point of any unit over any other unit, okay? So in this case, being saturated in terms of organic chemistry means each carbon has a max number of hydrogens. So if I have two carbons, Alpha, so what's the max number of hydrogens that can bind to these two carbons?
So it would be 3 on each side to 6.
Good. And when you do that, what type of homologous series is this? Is it an alkane, ene, or ine?
Isn't it alkane?
Good.
Yeah.
So that means all alkanes are saturated. They have the max number of hydrogens per carbon. But Alpha, the second I go from an alkane to an alkene, this is called ethene. How many hydrogens are bound to each carbon?
There's only 2 on each side.
2, right? Whereas we just clearly said there should be a maximum of 3 hydrogens that can bind to each carbon. Now, since there's less than 3, aka there's 2, because this double bond has occupied one bonding site, we call this compound unsaturated. Does that make sense?
Yeah, thank you.
So only alkanes are saturated. Good. Only alkanes are saturated. Good. Let's move on. All right. Nothing else to say so far, except this one point here. So in this hierarchy of naming, everyone, when we come down to numbering things, remember I told you we're going to number it left to right, right to left. We're going to count the number, and we're going to pick the lowest number and go that direction. Naming an alkene is actually much easier because when it comes to numbering and going left to right or right to left, you are always going to go the direction that gives this double bond the lowest number. So I don't care if there's a chlorine or a bromine or an iodine here or an ethyl group here, CH2CH3. I am going to go the direction that gives this double bond the smallest number. Okay, so how about we give it a go at naming this compound here that we see. Okay, and what I'll do is I'll actually make it a little bit different. We'll keep it at this. All right. How would you all name this? We're going to go A to B. We're going to name this just like an alkene, and I'm going to show you just the subtle differences with an alkene. It's actually easier to do an alkene. So I'll get one person to take it away from start to finish. Maher, start to finish, how do you name this?
I can't see anything.
Can everyone else see the screen? Gerald?
I think so, yeah.
Okay, Gerald thinks he can see the screen. What's going on? Are we hallucinating or? Okay, let me reshare. I think when the internet connection is not great, the screen might stop sharing on either end, if either of our internet is not strong. Okay, can you all give it a second? It should load. Okay, can you see the screen now? Maya?
Yeah.
All right, good. Maya, how would you name this hydrocarbon, start to finish?
Alright, so first we count the longest carbon chain.
Good. Now, the only
Um,
difference, everyone, is you're going to pick the longest carbon chain that has the double bond. Okay? So now it's not just pick the longest carbon chain. If the longest carbon chain was, let's say, it went down like this. Okay? You would make sure you go the direction which has the double bond. So you'd go down like that. Okay? So key point here is you want to pick the longest carbon chain with that double bond. The double bond can never ever be part of an alkyl group. It has to be part of the main chain. That's the first difference. Good. So longest carbon chain, Mahir counts 3. Mahir, you can now do the next step, which is numbering left to right or right to left. But logically, Mahir, which direction are you going to go? You're trying to give this double bond the lowest number. Which
left
end
to right.
is the double bond closest to? Yeah, it's closest to the left. So we're obviously going to be starting from left and going towards the right. So I'm going to name this carbon number 1, this carbon number 2, and this carbon number 3. Okay. Now, when it comes to naming alkenes, we need to consider whether to give the double bond a number and what number to give that double bond. So Gerald, you see that the double bond is between the first and second carbon. Now, IUPAC is all about the simplest number and the simplest formulae. What position is that double bond? Would you say that's in the 1
It'd be
position or
1.
2 position?
1.
Good. So you would say this is a double bond that's in the 1 position. Good. So 1. Okay. Now, on to naming. There are no substituent groups, which makes our life easier. And what is this main chain? It's 3 carbons and it's an alkene. So what do you call that?
Propene.
Good. So you call it propene. Now, typically what you'd do, everyone, is if it was a longer chain hydrocarbon, you would want to identify the position of the double bond. So you'd call this 1-propene to show that this is propene with a double bond in the first position. Or between the prefix and the suffix is another way to name it. You would add the number, and that's the more correct way. Both will get you the mark in the HSC. Ask it for your school, but most schools prefer the second way, which is prop is the prefix, "ene" is the suffix, so the number goes in between to show the double bond position. But I have a question for all of you. Do I need to state that the double bond is in the first position? Why and why not? And I'll give that question to Annette. Do I need to say 1-propene or prop 1-ene?
No, you can just say propene because you can, like, if you move the double bond to the other one, then like it doesn't make a difference.
Good, because if you move the double bond 1 position to the right, everyone, do you agree this is going to become carbon number 1? This will be carbon number 2, and it's still 1-propene, and the double bond can't move anywhere else. So that means there's no such thing as 2-propene or 3-propene or 4-propene. So there's no point putting a 1. And so we just call this compound propene. But I use the numbering just to show you what you do for a longer chain. Okay, so you'd call that propene. Same thing here. Jad, would you number this? Would you call this, it's 2 carbons, so it's an eth. It's a double bond, so it's an alkene. Would you call this eth 1-ene or just ethene?
Just ethene.
Good. Now, what about with this compound here? This one at the bottom. I want you all to name this and tell me. What would you call it? Would you call it... Yeah, just raise your hand once you got an answer. I will not spoon feed. Oh, very quick. Nice. Alphys, what are you calling this compound at the bottom?
Wouldn't that be butene?
You sure? Is butene? Again, the question is, do I need to number the position of
Oh,
that
wait.
double bond?
Isn't it the 1-butene?
Good. Right? Now, the reason is if I move this double bond, So I move it here. Creativity, just move it one position. What would you call this? Well, carbon number 1. If you're unsure, you can number it right to left and left to right. So I'll just do it just to show you. If you're stuck, number it right to left and number it left to right. Either way, the double bond falls in that second position, right? So it's not 1 butene anymore, as in the original question. It's now 2 butene, or but2ene. So that's a completely different variant of butene. So we do need to state the position of that double bond. In this case, it is a 1 butene, or but, prefix, -1, and the suffix, which is ene. I'd prefer you do this way. The HSC prefers you do this way. So does IUPAC. Schools vary. So ask your teacher what they prefer. Good. All right, good job. What I'll do now is I'm going to throw you in the deep end. You're going to start naming harder alkenes. So how about we do? This is a tough one. You got 2 double bonds, and you might wonder, well, I haven't learned this, but again, if you truly understand IUPAC, you can derive how they would name it. Remember, simplest structure, simplest formula. If there are multiple of a particular group, state the position and then state the quantity, just as you did with your alkyl groups. So once you got an answer to this, hit the raise hand icon. So Nat and Mahe, just put your hands down so I know. Thank you. Then you can hit your raise hand once you've got an answer. Okay, many people have got their answers, so I'll ask. And what's your final answer for this? Actually, Gerald, what's your final answer?
My final answer was 2-bromo -5,5 ethyl hex.
Ooh, 5,5 ethyl? If there are 2 ethyl groups, what would you call it? Would you call it ethyl or diethyl?
Yeah, diethyl. Sorry. Yeah, diethyl hex.
So, location, quantity. Whenever there are multiple groups, location, quantity. Okay, so you forgot quantity, get a red pen and circle that. So you don't that again. So it's 5,5 diethyl. Keep going.
Hex.
Yep.
Dash 2,3
Okay, now don't make the same mistake again. How are you going to end it?
dash ene dash
Come on,
diene dash
location.
diene. Yeah.
Good. Very good.
Bang.
Right? He's learning and evolving as he goes. Good. That is, I haven't checked the numbers, but it looks or sounds much more correct than the first iteration that you had. It's a good job. So again, did you all see it's the exact same principle? When there are multiple double bonds, you follow the exact same principles: location and quantity. Location, quantity. Okay. Mithilesh, did you get the same name?
Yeah, I got the same thing, except I just didn't know that you had to put a di in front of the ene as well.
Okay, good, good. Well, I guess this is a good learning
Oh,
question. Now, just a small tip.
Put dimethyl. I put dimethyl, not diethyl.
Yeah, same with me. I got dimethyl.
Yeah, I can see that right here. There's only ethyl groups. I don't see any. Sorry, there's only methyl groups. There's no ethyl groups. So yeah, I would agree. It's probably dimethyl. Dimethyl. Gerald, did you accidentally see that as a methyl group? What happened?
I think I just brain faded. I'm not too sure actually.
So make sure you search it, right? And make sure you shouldn't even use this. You should have redrawn this as a full expanded structural and then gone through the question, which would have made it much easier.
Yeah.
Annette, did you get the same answer?
Yeah, I got it as a methyl.
Good. And does anyone want me to go through this? I'm more than happy to.
Yes, please.
But I also understand most of you are quite good at chem. Mahe, would you like me to go through this by any chance? I see you. Okay, perfect.
Yes.
All right. So Mahe, you're going to help me with this question. So I want you to imagine I'm here at school. I have no clue how to do this. You can teach me. What do I do? What's the first step?
Carbon chain.
Yes. Before that, we see a funky skeletal formula. Convert it to a full expanded formula, right? So I'm going to redraw this. Carbon, carbon. There's a double bond and another carbon. I'm just following this method, right? Carbon, carbon, double bonded carbon, another double bonded carbon, another carbon, and then another carbon here. This looks like a methyl group, everyone, but I want you all to just realize that's just the final carbon of a chain, or that could be the final carbon of the chain. They've just drawn it. They're switching. Do you see how they're going from a completely skeletal diagram to a condensed diagram? They love to do that in the HSC to trick you. But this could be part of the main chain. It doesn't have to be a methyl group on this side. So just keep that into account. So that's why we're going to redraw this. Now, I see at the second carbon position, 2, there's a bromine. I'm going to draw that up there. I see at the third, fourth, fifth carbon position, there are 3 carbons attached. So the first, second, third, fourth, fifth, I see the first carbon attached here already. So I'm going to draw 2 more carbons attached. So one more carbon. And so that's the structure that I'm going to be naming. Now, you're completely right. Longest carbon chain with the double bonds. So I'm probably going to cross. Now, I can choose to go up, across, or down, but does everyone agree it doesn't matter which way I go? Right? It's still going to be the same number of carbons. So I'm just going to keep it simple. I'm just going to go right across. Okay, what do I do next, Alphys?
What did you find? Like, try to find the lowest number for the double bond group.
Good. Like I told you guys, normally we won't have to number it left to right or right to left because alkenes would be smaller in size and they wouldn't see how the double bond's kind of the middle of this molecule. You can't just eyeball and say we're going to go left to right or right to left. So in this case, to be completely safe, I am going to number it both ways. It's a good call. I'm gonna number it 1, 2, 3, 4, 5, 6. All right, and a little tip: circle the substituents as well so you don't make silly mistakes. Alphys, if I go left to right, which is green, what's the total sum? And remember, now you're not going to sum the alkyl groups. You're summing the double bonds. They have much, much higher priority. So alkyl, if I go left to Alphys, if I go left to right, what's the alkyl? What's the double bond number?
Wouldn't it be just 2 plus 3?
Yep, 2 plus 3. Very good. He's given the lowest number to the
It
double.
would be 4 plus 5.
Good job.
I mean,
Perfect.
no way, isn't
Right
it?
to left.
3 plus 4.
Oh, yes, you're completely right,
Yeah.
because this double bond is between the third and the fourth. It's a 3 plus 4. Good pickup. The 3 plus 4. So you can clearly see we're going to pick the green. So I'm going to rub out the red. Useless. So we're going to pick the green direction. Now it just comes down to naming in alphabetical order. So to be safe, what I like to do is I add the initials. So this is a B for bromo, and then the M's for the two methyls. And then I go, okay, well, since I'm going left to right, there's a bromo in the second position. So I'm going to call this 2-bromo. And Mahe, where are the methyl groups? Because those are the only other two.
5 and 5.
Good. So I'm going to put a dash 5, 5. And since there's two methyl groups, what I'm going to put in front of the methyl?
Di.
Good. Dimethyl. And then I ask myself, are there any more alkyl groups? No. So now I can name the main chain. The main chain is 6 carbons. What's the prefix for 6, Maya?
Hex.
Good. Hex. 1, 2, 3, 4, 5, 6. Very good. And there are two double bonds. So I'm going to put dash. And what's the position of those two double bonds? What did we say?
2 and 3.
Good. So 2, 3. And what are you going to end it with? It typically ends as ene, but since there are two double bonds, what are you going to call this?
Diene.
Good. Diene. Very good. And that is it. That's the naming for this alkene. Now, again, you'll never get a question like this in the HSC, but in trials, you definitely can. Yeah, but I can guarantee you'll never get two double bonds in an alkene. But this is just so no matter what hydrocarbon you get, you have a very strong naming principle and structure. And this is really important, guys, because in Mod 8, there's technologies that identify the different variants of hydrocarbons. And you need to be able to think very visuospatially as to how these technologies will pick it up, how they will show differently in terms of their graphs and tables. So it's really important to understand this. It links onto 8 as well, which is arguably, I'd say, the most high-yield module of all of HSC Chem. Any questions so far? Good. All right. You tell me, what would you all like? Moving on to alkynes. Alkynes, I'm going to spend a very short amount of time on it because you just don't get alkyne questions in the HSC, and it's very easy as well. So you tell me, would you like to do one more practice question for alkenes, or are you happy to move on? So hit the raise hand icon if you're happy to move on, and keep your hand down if you want to do another practice question. Good. All right. Happy to move on. Power through. I like that. All right. You can do all these questions in your own time then. Just before we go into alkynes, actually, I will go through alkynes, then I'll go through how to draw it. All right. Now, alkynes, very quickly, they consist of the triple bond. The general formula is CnH2n minus 2. And at which cyclic hydrocarbon family has the formula CnH2n minus 2?
The alkene.
Cycloalkenes. Very good.
Yeah.
Cycloalkenes are the same formula as alkynes, which is CnH2n minus 2. Very good. And alphas, are these saturated or unsaturated, and why?
Well, they're unsaturated because they don't have the maximum amount of hydrogen connected.
Per carbon. Yeah. Remember, it's always per carbon. Per carbon, we need the max number of hydrogens. In this case, we don't have that. Only one hydrogen can bind to each carbon. Have a look at that. Per triple bond, right? In this structure here, with a CC with a triple bond in between, only one hydrogen can bind to each carbon, whereas in alkanes, it could be 3. So it's a clear unsaturated compound. Good. All right. Naming, I'm actually not going to go through naming because if you know how to name an alkene, you can name an alkyne. The only difference is instead of ene, you add "-ine" at the end. So here's your first one. Name this for me. You will have, I don't know, 20 seconds. Try eyeballing this in your head, actually, because you don't really need to draw anything. So, Risat, what's your answer for this compound?
One butane. Sorry, is it 4? Yeah.
Good. So my structure would be, this is how I'd break it down in my head. What's the longest main chain? It's clearly this. There's no other carbons. So it's 4 carbons. I know it's a boot. And there's a triple bond, which tells me it belongs to the alkyne family. It's a butyne, right? Are there any alkyl groups? No. Do I need to number it? Since it's small, since it's 4 carbons, I should ask myself, do I need to number it? And to answer that question, Gerald, what do I do?
Yeah, you do need to number it.
You don't? You do. Tell me why. How
You
do
do.
how do you answer that question?
Wait, you do need to number it.
You're right, but I'm asking you how. I know.
Oh, yeah, you
I'm
just
stuck in
visualize in other.
Good.
You
That's it.
visualize
So you
in other
visualize-
positions.
Good. So move it around, and here, if it goes there, it goes to second position because this is carbon 1, this is carbon 2, 3, and 4, right? So if this double bond or triple bond moves, this will become 2-butyne or butyne. So since the name changes, yes, I do need to number it. So this is going to be 1-butyne or but-1-ine. One tip, guys, just be very careful where you put the number. Okay, and the way you remember where to put the number is between the prefix and the suffix. Do not put it anywhere else. Okay? If you put bu-1-tine, that's completely wrong. That's why you need to be very cautious. Okay? Good. Now, small point. Only because I've seen this come up in trial papers and students complain they've never ever seen this before. Your teachers aren't expected to teach you this, but it can come up in your exams. And this is the fact that they'll ask you what the bonding angle is in certain carbon-hydrogen arrangements. So although everyone, we draw your methane like this in your notes, you need to realize this is not actually how methane's bonds are present. Just wait for it to load. Wait a quick second. Okay. Just while it's loading, what I've drawn is methane with its bonds, each carbon-hydrogen bond at a 90-degree angle, right? Now, yeah, so you can see that now. That's not actually how methane looks because in reality, molecules are in a 3-dimensional space-time continuum, right? What this means, remember, going back to Vesiper theory, let me get, Mithilesh, what is Vesiper theory?
It's like the polarity of molecules.
Using fancy words to explain another fancy word. Vesiper theory is valence shell electron pair repulsion theory. Now, it's the only fancy word I'm going to use. What this pretty much means is electrons hate each other, right? So remember, every single line you see here is an electron pair. Every single electron pair hates the other electron pair because they have the exact same charge and thus will repel via electrostatic repulsion. What that means is if you let these bonds freely exist in space, they will move as far away from one another as possible. Now, the one thing we're not considering is the bond can also move towards you, which is out of the page, or away from you, which is into the page. So this looks like the bond should be 90 degrees apart from one another. What actually happens is this bond here, imagine it moving out of the page and smacking your face. So it moves in that direction, and these two bonds will also move backwards, such that we have what's called a tetrahedral arrangement. So this is a true structure of methane, where this bond is coming out of the page, these two bonds are going backwards into the page, and this bond is going straight up. And what that does is it makes the bonding angle 109.5 degrees. So you should know the bond angle for a tetrahedral molecule, such as methane, is 109.5 degrees. Mahi, a question?
Sorry, I had a problem before.
Okay. All right. Yeah, just hit the, bring it down, because otherwise it just looks like your hands are raised permanently. All right, next. Now, with this molecule, can anyone tell me what is this called? This structure here, where you have this bond angle that's actually, yeah, I kind of gave it away. It's right here, planar. This is a trigonal planar geometry. And this occurs when you have, you could either have 3 bonds, so it can be 3 bonds, single bonds like that between molecules, or it can be two bonds, two single bonds and one double bond. So I guess the key example of this, the reason this is important, is one of the most important molecules on this planet is ethene. And we all draw ethene like this in our exams. But in reality, ethene structure more correctly should look like this. Because remember, these two bonds hate each other and will repel away from one another. So ethene actually has this structure here. And if they ever ask you, and this is literally what they asked in one of the exam choice trial papers, what is the molecular geometry of ethene? And the answer was ethene forms a trigonal planar molecular geometry. Okay, so remember the answer here, especially for ethene, is it forms a planar geometry. Very important. Any questions so far? Good. The rest, very easy. Not going to go through them. Any other one, a unique bonding arrangement between carbon and hydrogen is linear. So don't even memorize that. Just should make logical sense.
We need to memorize
Okay.
the angles.
The angle's not so important. See, this one is logical, right? Because this looks like a pie. And if you break a pie into thirds, it's 120 degrees, right? So I would say you should memorize tetrahedral and planar, but yeah, the rest is just 180 degrees. So I guess to answer your question, technically you should. But the only one you really need to memorize alphas is this. The others are all logical, right? If you have a pie graph in thirds, it's 120 degrees, and the others are 180. Good. All right, we'll move on. Skip cyclic because we've already shown you how to name it. Let's go to naming. Let's go all the way up. Sorry, drawing. Let's go up here. Now, the reason I kind of skipped this is because it's very easy drawing hydrocarbons, but I'll just show you the steps very briefly. Let me go to some names. Let's see. All right. And before you take your break, I want you to draw this structure. Go straight to it. Just give it your best go. New book. How did you name this? If you can name that, sorry, draw it. The name's already been given. If you can draw that, you can draw any hydrocarbon. Drawing is not a hard aspect. But hit the raise hand icon once you've drawn it out for me. You guys remember? Yep.
What do we use structural or like which thing do we use?
Always expanded structural. Always expanded structural, right? Even if it's the day of a HC exam when you revised everything, if you're ever asked to draw, which you won't be because it's too easy to draw hydrocarbons, expanded structural. The time this becomes important, guys, is in Mod 8. They give you graphs, and you have to use technology graphs such as spectrographs to draw and identify the hydrocarbon. So that's the only time where this is examinable. You never get a question this easy otherwise. Okay, hit the raise hand icon once you've got an answer. All right, good. Most of us have named it. Now, what's the principle? What would you say are the steps to draw a hydrocarbon so you never ever make a mistake? Annette, what are the steps in your head?
Well, I started with the last word, so it's a nonane. You can
Good,
tell
so
that.
name. Good. So what do? You draw the nonane, which is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. What do you do then?
And then I guess you can label the carbons.
Not even you can, but you don't have to label it left to right and right to left, because you can arbitrarily say my left carbon is carbon number 1. And then everything is based off that, right? So just looking at the naming, there's a trichlor at the second, fourth, and fourth. There is a 3-ethyl, so go to the third carbon and then add a. Now, I guess the only thing, guys, is when it comes to alkyl groups, do the expanded formula still, so you don't make mistakes just yet. But what you'll notice is the final carbon has 3 hydrogens. The carbon in between only has 2. So if it was to be drawn in condensed form, it would be CH2 line CH3. Okay, good. So we're going to add the substituents. What else do we have? 3-ethyl, we have 6-methyl. So at the 6th position, 1, 2, 3, 4, 5, 6, we're going to add a methyl, CH3. Now the last thing you're going to do, just one small tip, make sure everything is expanded or condensed. Do not change parts as expanded, parts as condensed, or you'll lose marks. The final step is you fill in hydrogens. And this is usually where students will make mistakes. The easiest step, right? Because it can easily be incorrectly added. The final carbon will have 3, the others will have 2. So make sure you do that accordingly, like that, and then fill it in with a hydrogen. Okay, just make sure you don't make a silly mistake and add an incorrect number of hydrogens. Good. I think on that note, I'll give you all a 5-minute break. Let's recap at 7:15, and we will continue on. We'll move on to properties of your alkanes, alkenes, alkynes. We're doing really well. Good job. All right, see you guys in 5 minutes. All right. When we're back, let me know. Turn on your cameras and we'll jump right into things. What we got now? Okay, one small point I'll mention just so we can keep perspective on things is that what I've actually done is I've actually jumped a little bit when I spoke about hydrocarbons. Because when you talk about hydrocarbons, there are two different categories. And one of those categories can then be broken down into your alkanes, alkenes, and your alkynes. And what I'm talking about here are your aliphatic hydrocarbons. There are also another group of hydrocarbons called aromatic hydrocarbons. And the reason they're called aromatic is because, quite simply put, they all have an aroma. And the reason they have an aroma is because of a very specific and important functional group. Now, you'll see this functional group a couple of times, but this is just to highlight to you how important it is in organic chemistry that we literally created a divide in hydrocarbons as to whether they have this functional group or not. And the functional group I'm talking about, everyone, is this ring consisting of 6 carbons like this. Jared, what would you call this group right here that you see in front of you?
Cyclohexane.
Good. Now, what's going to happen, everyone, is I want you to imagine that every second carbon has a double bond like this. Right? Now, what actually happens in this arrangement is these two electrons, and these two electrons, instead of staying in one spot, they actually keep moving around in a ring-like arrangement. They form this inner cloud of electrons. And so you'll often see that drawn as this. Okay, so the expanded structural formula will look like this. You may also see a simplified structural formula that is just drawn like this ring with a circle inside. The circle represents this cloud of delocalized electrons. Delocalized electrons. Now, any hydrocarbon that has this structure completely changes its properties beyond the scope of what you'll learn in year 12 HSC Chemistry. And the functional group that this molecule goes by is benzene. Has anyone heard of benzene before? It's carcinogenic. You find it in cigarette smoke, but it's actually a very, very important molecule in itself. When it's attached to a hydrocarbon, it completely transforms the properties. And so any molecule in organic chemistry that has a benzene ring is immediately called an aromatic hydrocarbon. When it doesn't have a benzene ring, which is what you'll be studying in the HSC syllabus, it's called an aliphatic hydrocarbon. So in the HSC, you're only studying aliphatic hydrocarbons, so actually just zoomed in here. But just realize there is this whole group that studies benzene. And you will need to learn about benzene when we talk about polymers at the end of this module, because we can add benzene to plastics to completely transform the plastics properties. We'll talk about that soon. Good. Now, this is a very high yield part of the module. And I would say, even more important than naming, this is typically where students can also make a ton of mistakes. I remember when I sat my trial exam for chem, I got one question wrong, and that one question was an isomer question. It was a silly, silly mistake. So just to put things in perspective, isomers are a very integral part where you should not make mistakes. And the way you can do that is having a very systematic approach. Now, let's define what an isomer is, right? You would have learned this in year 11. What's an allotrope? We'll know what an allotrope is. Alphys, what's an allotrope?
Two or more different physical forms. One element can like exist.
Of a
Element.
Yep, two or more physical forms of what? Yeah, good, an element, right?
Yeah.
So if I said carbon, Alphys, what are the two allotropes of carbon that you know?
Wouldn't it be graphite, charcoal, and diamond?
Good, diamond, graphite. Charcoal, not really. Charcoal is just carbon soot. But diamond, graphite, and
What's
fullerenes
full-
is another example. But
Fuller.
good, Buckminster fullerenes, good. Anyway, coming back to our point here, isomers are similar to allotropes, but allotropes are variants of an element. Isomers are variants of a molecule. So the way you understand this is an isomer is any compound that has the same chemical formula, but different structural formula. Different structural formula. That's it. That is what an isomer is. The definition's easy. The hard part is identifying all the different isomers of a molecule. So guys, if I say C4H8, give it a go. I want you to just literally freehand it. How many isomers do I have for C4H8? So this is the same chemical formula. You must have the same chemical formula. But how many different structural variants can I have of this? I'll give you all a minute to just freehand, think critically, think visuospatially, move the molecule around. Pretty much, if you've seen Iron Man, what Iron Man does to, when he gets a three-dimensional prototype and moves it around space. Same thing with this molecule. Move it around, move the functional group around, add alkyl groups, remove alkyl groups. Tell me how many different variants you can come up with. Those of you who can think more visuospatially will do good with this question. Not that there's too many variants for this one here, but I'll give you a harder one after this. Hit the raise hand icon once you think you've exhausted all your options. And there aren't too many for this one specifically. I'll just get some water. I'll be right back. Actually, I might start by just going through this one with one of you. Let me go with Anna. Anna, how many examples can you think of just off the top of your head? And how are you breaking this down?
Well, I did it with, like, the first thing that came to my head was a cyclic same kind of idea. And so I did 4 carbons in a circular ring and the 2 hydrogens coming off of each carbon.
Oh, insane. Okay, good. Good. Now, I'm just going to preface this, guys. In the HSC, they'll only ask you linear isomers. So, Annette, you've actually thought a whole level deeper, which is very good. I'm very happy with that. But you are right. You're not wrong. That is definitely an isomer of C4H8. But again, in HC exams, they won't count this necessarily as an isomer, only because they don't expect you to know cyclic isomers. They only expect you to know straight chain isomers. But very good. Good job. I agree. That is, under the definition, perfect. It is an isomer. But let's move on. Let's think about more linear ones. So, Mahe, what are you thinking?
Like how many I got?
Just give me some isomers. Tell me what I should draw.
Um,
I want to see your
so I guess
thinking. That's what
so I drew like a chain of 4 C, like 4 carbons.
And then?
Um, And then I put like 2 hydrogens attached to the ones on either end.
Okay. Like
Okay.
this. Okay. Like that.
Yeah.
That doesn't make sense to me, because why would there only be 2 hydrogens on either end when technically a carbon can bind to 4 hydrogens in total? So there should be 3 at the ends. Right?
Yeah, true.
Okay. That's all right. Mithilesh? What do I do?
So I just put a double bond, just in one place.
Good, because Mithilesh has picked up that C4H8 represents an alkene, right? So we must be operating within the realm of alkenes. You can't make an alkane. An alkane will be C4H10 no matter what. So we have to exclude our alkanes, exclude our alkynes. All right, so you can add a double bond. All right. So that's one variant. What else can we have, Mithilesh?
We can have the double bond in the middle.
What are the variants can we have?
Double bond in the middle.
Good. So you can start naming. Good. So it could be 1 butene. We could have a 2 butene. Good. Mithilesh, if I put the double bond in the end like this, would that be a whole other isomer, or is that just one of the above isomers?
It's just a rotation of the first one, so it's the same thing.
Yeah, it's the same thing. This is where visuospatial understanding is important. This is in the first position. This is also in the first position. If you just flip it 180 degrees, right? So this is why it's so important. Okay, so that's 2 isomers. Can anyone think of any other isomers? Anyone think of any more? Because there are
Triple
more.
bonds.
Not triple bonds, because the second you have a triple bond, you have an alkyne. The second you have an alkyne, it's going to be C4H6. Do you agree?
I'm not
All
too
right.
sure.
So do you guys see why it's hard to identify all the isomers? We're actually missing, I think, one more isomer.
Wait, I
Yeah,
don't know about
alphas.
this one, but could you put the carbons in like a square?
Have the carbons in like a square. That's a cyclic hydrocarbon if you form a square.
Oh,
So
okay.
sorry, and that I added way too many carbons. I should have just done it like this. You're right. This should have just been C like this.
Oh,
This
that's
is a
okay.
cyclic hydrocarbon. Yeah, I added like 6. I'm sorry, guys. I always think of hexane whenever I draw it, so I intuitively went there. But alphas, yeah, you pretty much have got what Annette said, which is CH2, 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 CH2. Square pizza. All right. We're all missing one, and I'll show you how to not miss it, but I just want you to appreciate how easy it is for you to miss isomers if you don't have a systematic approach. Did you all see that? We all missed one isomer because we didn't have a systematic approach, and this is what I'm here to teach you. Sorry, could you repeat that?
Is it based off of the position of the hydrogens? Like the
Not off the position of the hydrogens, because remember, the position of the hydrogens will never affect the naming. That's why I never draw hydrogens, and that's a tip for isomers. Never draw hydrogens, because you're just wasting time at that point. So let me break down isomers, and this will teach you how to make sure you never miss an isomer again. So when we say the word isomer, everyone, there are 2 kinds of isomers. And guys, make sure you, if I'm cutting off, do let me know. I think there's just a bit of a lag. That's why I'm answering you maybe a bit slower than you anticipate, or I'm understanding what you're all saying a bit later. But I think there's a little bit of a lag. But otherwise, I hope you can all hear me. So when it comes to isomers, there are 2 kinds. Okay. And I'm actually going to structure it a bit differently. You have your, maybe I'll do it like this. You have your chain isomers. And you also have what you call your positional isomers. Positional isomers. Okay. And in a whole other category, in fact, we can draw it like here, the isomer, we have what we call functional group isomers. Functional group isomers. Now, the reason I've drawn this in this funny way is to show you they're not actually three separate categories, but they're mini categories under a particular category. So when we see the word isomer, we have what we call different functional group isomers. Within functional group isomers, we have chain isomers. Within chain isomers, we have positional isomers. So that's the kind of hierarchy or categorization. And let's start by defining what we mean here. So if I see something like this, right? If I see say a C4H10, I'll do H8O. If I see something like this, guys, what I would do, now you've never seen an oxygen, but this is just to show you what a functional group isomer is. What this could mean is we could have potentially a 4-carbon main chain, and we could have a double bonded oxygen at one of the carbons. Okay, and that's what we'd call an aldehyde or a ketone. That is its whole other functional group. I can also have a completely different functional group. Have a look at this, a completely different functional group. I have an O and an OH at the end, right? And so that's a completely different functional group in itself. It's what we call a carboxylic acid when you have a double bonded O and an OH. Again, you don't need to know any of this, but this is just for me to show you. Later on, you will learn that there are many different functional groups we can have. Okay, for now, it's very simple. The only functional groups you've learned are the single bond, the double bond, and the triple bond. So it makes life a bit easy for now. Now, within a functional group, right? So using our example of C4H8, do you all agree there is only one functional group isomer that we can have? And the only functional group isomer we can have is that of a alkene functional group. Everyone with me so far? That is the only functional group that can be present, because all you've learned is a single bond, double bond, and triple bond. Okay, this has to be a double bond hydrocarbon because of the proportion of carbons to hydrogens. Now, within that alkene functional group, there can be different chains, right? So we can have a chain consisting of 4 carbons, like this. So we can have a butene chain. But the chain that we all missed, guys, this is referring to the longest main chain, is we can have a chain like this. Don't you all agree? I haven't drawn the double bond. The double bond is just going to move around. But does everyone agree? This could also be a potential chain. This is a 4-carbon chain. But Gerald, if I was to count the longest continuous carbons, what number do I get to?
3.
Exactly, right? So do you guys agree? This is a butene main chain. I haven't drawn the double bond again at the top. And then at the bottom, we have what's a methyl propene main chain, which is what you're all seeing. Again, above is that butene chain, and then below you have the methyl propene chain. So those are 2 different chains, so butene and then methyl propene. Since they're 2 different chains, those are the 2 different chain isomers underneath the functional group alkene. Does that make sense? Now we're starting to understand that we have functional group isomers. Underneath that, the different longest main chains are called chain isomers. Now I want you to fix one main chain. So we're either going to look at butene or we're either going to look at methyl propene. So Annette, pick one to zoom into and explore further. Butene or methyl propene?
Methyl propene.
Okay, she picked this slightly not challenging, but just the non-conventional one. Methyl propene, right? Now I told you, well, there has to be a double bond here, right? So now what I'm going to do is I'm going to find all the positions of the double bond within that chain, aka zooming back out. What did we say? Within our chain isomer, we'll be exploring now all the different positional isomers. So positional isomers refer to the position of the functional group. In this case, the functional group is a double bond. So within the methyl propene chain isomer, we can have a double bond here. What would you call that, everyone? If the double bond was there, what would it be called? Quickly. 1-methylpropene. Does everyone agree? This would be carbon 1, this would be carbon 2. Okay. Actually, let me pause for a moment. I don't want to. Should not be 1-methylpropene. I have a question for you all. Do I need to say this is 2-methylpropene? Do I need to call this 2-methylpropene? Any ideas? Forget about the double bond. I know this should be 2-methylprop-1-ene, but I'm asking you about the 2-methyl. Do we see that methyl group there? Do I have to call that 2-methylpropene?
Yes. Oh no, wait.
Okay, to answer the question.
No, you don't.
Yeah, the answer. Yeah, see, we'd think that superficially, right? And you'd actually be okay not to include the 2-methyl. But technically, this is the thing, guys, with IUPAC, with the alkyl groups, especially for a linear chain hydrocarbon, they care about the numbers. You need to always have numbers for alkyl groups for a linear hydrocarbon. Remember, when we are doing our cyclic hydrocarbon, we didn't need to state the position of the chlorine or the bromine because there is no carbon 1. Carbon 1 is arbitrary, right? So there you can just call it, in this case, sorry, there's a bit of a lag, I think, from what I'm drawing and what's popping up on my screen. So give me one quick second. It's really annoying me. Okay, can you all hear me fine now? Okay, and tell me if you can see my screen as well. Can you all see the screen a bit better?
Can't see the screen.
Give it a sec. Okay, can you see the screen at the moment, guys? You should be able to. All right, good. Okay, so like I was saying, the only time you don't need to state the position of an alkyl group is when it comes to cyclic hydrocarbons. When there's only one alkyl group, you can just call it cyclohexane, such as in this example. Now, the time we have to ask yourself, do I need to number, is when it comes to the double bond, right? Remember when we're doing a propene, for example, this is a propene main chain, the double bond being here or the double bond being there, it's still called propene or 1-propene. So we don't include the numbers. But the last piece of tip I'll give you is when it comes to linear alkanes, you must always state the alkyl group positions. Okay, so yes, TLDR, cyclic hydrocarbons, you may not need to state the position of the alkyl groups. Double bonds, which are functional groups, you may not need to state their position. But in a straight chain hydrocarbon, which is what you'll be working for in the HSC, you always must state alkyl group positions. Does that make sense to us all? Okay, so you can see here I've not numbered the double bond position. And we'll talk about that now as well. So this is always going to be a 2-methyl propene. Okay, Now, Gerald, if I move this double bond from here to here, what would we call this this hydrocarbon? It was 2-methylpropene in the first position. What if I move it there? What would it be called then?
It would still be called 2-methylpropene.
Perfect, right? So now Gerald understands the main chain will now be this. Even though it's bent, it's still the main chain because it has that double bond. And the double bond is between the first and the second carbon. So it's still a prop 1-ene, so we don't need to number its position. And there's a methyl group at the second carbon, 2-methylpropene. Now, the final thing I'm going to do is I'm going to move that double bond in the final position. If I move it there, with less, what will it be called? Longest main chain is now here.
That's still 2-methyl.
Good. So does everyone agree there's only one positional isomer under the methylpropene main chain? Okay, so the main chain here is a propene main chain, and there's only one positional isomer under this chain isomer. Okay, so I'm going to just label this as 1. Good. Now coming back up here with butene, this is a bit easier. And that's you you start us off with the harder one, but it's my fault because I gave you the option. So now it's going to be easy, guys. So don't get intimidated by this. But now with a butene main chain, it's much easier, right? You can't change that main chain because we're focusing on that main chain. We're going to find all the positions that a double bond can be in. If the double bond is in this position, so in the first carbon, Risa, what would you call this?
That'd be but1-ene.
Good. And Risa, what if it moved to this position? They move from here to here. What would you call that?
but2-ene.
Good. And remember, the goal with isomers is to be meticulous. You will miss if you aren't meticulous. So move it in the third position. Some of you know this won't work. Risa, what would you call this?
but1-ene.
Very good. So now everyone, what are the total number of isomers? Does everyone see? In total, there is 1, 2, 3 isomers. But1-ene, but2-ene, and 2-methylpropene are the 3 different isomers of C4H8. That's the total number of isomers. Now, Alphys, if the question asked you how many chain isomers are there of C4H8, how many chain isomers do we have?
Chain. Is it 2 chains?
What were the 2 main chains?
Wasn't it butene?
1 chain,
and
a
methylpropene?
and then a butene main chain. Very good. So there are 2 different chain isomers. Within the first butene chain isomer, there are 2 positional isomers. Within the propene chain isomer, there is 1 positional isomer, which is 2-methylpropene. Okay, so now do you see why I've drawn it in that structure where I put functional group isomers at the top? There's only 1 functional group isomer. It's the alkene functional group. Within that, there are 2 different chain isomers we can have. For the first chain isomer, there are 2 positional isomers. Second chain isomer, there's 1 positional isomer. If the question ever asks you how many isomers, full stop, okay, they don't specify if they're talking about functional group, chain, or positional. They're talking about positional, right? So the final variance here. So we've got 2 variants at the top, 1 variant at the bottom. So we'd say there are 3 isomers total. I know that's a lot, but that is isomers, and you only get better and better from doing examples. So how about this, everyone? Here's an example for you. This is what I had in my exam, which I unfortunately missed an isomer for, which is C4 H9 Br. Give this a go. I made a silly mistake. Hopefully none of you do. Question is, what are all the isomers of C4H9Br? And I want you guys to be like be like me in the sense that I'm 6 or maybe 7, many years out of the HSC, and I'm still traumatized by the one question I didn't get in my exams. That same way, if you approach chemistry in the sense that you make sure you never make that same mistake again, I can almost guarantee you'll get a high band 6 or at least a state rank. Okay, chem is not hard. It's just all about being meticulous and not being overzealous or confident, because a lot of people, a lot of students, once they get pretty good, get confident and complacent, which is probably the biggest selective school weakness that I see. All right, hit the raise hand icon once you've got an answer. Most of us have got an answer. I care more about your approach than your number, because the number can be correct or incorrect depending on the day. So let's see how our approach is. We'll start with Maya. What's your approach? Tell me your plan.
So first, I just drew the carbons out.
Sorry, what's the first thing you did? Maya disappeared. Oh no. All right, Gerald. Hopefully you don't disappear on us. What's the game plan?
First you find the functional group.
Good. So what is a functional group here?
Alkane.
Good. I'd say there are two functional groups. It's the alkane functional group, which is the main one, and then there's your substituent, which is your halogen. But you're completely right. This is an alkane functional group. In fact, technically you call this a haloalkane functional group. But yeah, good. All right, so we've got an alkane functional group. Within a functional group isomer, what are the variants we can have, Gerald?
You can have a butane, or you can have a 2-methylpropane, 2-methylpropane.
Good. So now Gerald's going, okay, well, I've got my functional group. What are the different chains I can have? Longest main chains. Now we can clearly see with a 4-carbon structure, we can have 1, 2, 3, 4 carbons, or we can have 3 carbons as the main chain with a methyl. So you're completely right. The 2 different chain isomers is now butane and 2-methyl propane. Very good. He's learning from the last question as well. You must add the 2. Okay, good. So now we'll move on to restart. Focus on one of them. We'll focus on the easier one this time. Butane. What are the different positional isomers? In fact, what is moving around? Because I told you, we never draw hydrogens. If you notice from the previous question, I never drew hydrogens for isomers.
The bromine is moving.
Good. So literally, guys, what you have to do is you need to be super meticulous. Put the bromine in every single position. So reset. If the bromine was here, what would it be called?
It would be 1 bromo. Well, 1
Good.
bromo.
So just call it 1 bromo because you know the main. Good. So just call it 1 bromo because you know the main chain is butane. So don't waste time writing butane every single time. So this could be a 1 bromo. Now reset. What if it was in this position?
2 bromo.
Good. Be meticulous. Keep going. What if it was in this position?
2 bromo.
Good. What if it was in that position?
1 bromo.
Good. So do you see how I'm being meticulous? Even though we know that if we go towards the right, it'll reform 1 bromo, still move it around so you know you've gone through every single option. Good. So now we've exhausted. Now we know there are 2 positional isomers within the butane chain isomer. Now Mithilesh, within the 2-methyl propane, how many different what if it was here? What would you call this?
1 bromo dash 2 methyl propane.
Good. What if it was here?
2 bromo.
Good, right? So make sure you guys are doing like renaming it. So if it moved here again, what's step number 1? Find the longest main chain. Longest main chain, simplest one could be just across like that. In that case, this is in the 2nd position. So it would be 2 bromo. Very good. What if it was here, Mithilesh?
1 bromo.
1 bromo again. This would be the longest main chain. This would be 1. That's how you'd quickly check. And what if it was here, being meticulous?
1 bromo.
Good. The longest main chain would then be that. Good. So now we see there are 2 positional isomers under 2-methyl propane, 2 positional isomers under butane. What's our final answer? What are the total number of isomers in it?
4.
4. Very good. 4 is the answer. I think I wrote 3. It's a silly mistake. All right. Reset. How many chain isomers are there and how many functional group isomers are there?
Chain isomers 2.
Good. And how many functional group isomers?
2.
Oh, when I say functional group isomers, I mean the main functional group, which is that this is an alkane, or you can call it a haloalkane, but that's just one functional group. Does that make sense? That's okay. You haven't learned the other functional groups, so I understand you don't understand what your sample space is. But so far, the only functional groups you've learned are alkanes, alkenes, alkynes. And out of those 3, this is clearly an alkane, so it's only one functional group isomer. Okay, good job. Any questions, everyone? Good. So now you understand how to break down any chain to find the isomers. Now, little tip, they won't ask you for isomers beyond C4. Because if you actually look at it, the number of isomers as carbon chain length increases, if this is carbon chain length on the x-axis, the number of isomers exponentially increases. If I gave you the isomer C5H11, Br, you would notice there'd be way more than 4 isomers. Okay, and it would keep on going up like that. So in the HSC, if you can do this well, you're set. This doesn't get any harder than this. Any questions, everyone? Good. Don't worry about cis isomers and geometric isomers. That's out of the syllabus. It's just interesting points because when you go to university, they do ask about that stuff. Question?
Could you just quickly explain what a functional group isomer is again? I kind of
Yeah, no worries. Again, like I said, you'll learn much more and you'll understand it better when you learn about other functional groups. But reset, there are only 3 functional groups you've learned so far. There's alkane, alkene, and alkyne functional group. For this molecule, is it an alkene, alkane, or alkyne?
Alkane.
Good. So we know it's an alkane, so that's the functional group isomer. It can't be an alkene or an alkyne. The halogen group is a functional group, but do you all see when there are 2 functional groups, the functional group of highest priority wins when it comes to naming the structure. So in this case, the carbon-carbon single bond has higher priority than the halogen group. So the halogen group becomes what's called a substituent group. Does that make sense? It doesn't impact the actual suffix or ending of the molecule. The molecule will still end in -ane. Does that make sense? Okay, so we just say there is one functional group here, which is your alkane functional group. Again, functional group isomers, will come back to it when you learn other functional groups. It'll make much, much more sense. Okay, but does that make rudimentary sense to you?
Yep.
Good, good. All right, guys, I think we're done on that note. We've gone through the different isomers. Don't worry about cis and trans and all of that. I've even broken down exactly how to identify isomers. This is my step-by-step guide. So what we just learned, I just wrote it down for you to go back if you're stuck. My tip to you is do all the isomer questions you can until you're very, very confident. So the isomer practice questions, please do. We've already done 1A. Do B. Do C. Do D. Do all of them. Make sure you do that. I'll ask you next lesson. I'm going to put a red marker here. Ask. Homework. 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 You'll get access to the booklets online, so don't stress about that.